All right, good afternoon, everyone. So, if you're at home today, right, this is the short video that you'll be watching, and it's really just about a short topic that the AP exam will probably spend a very short amount of time on, if potentially no time at all. You may actually not even see a question about this, but it is an important topic for a couple of reasons, and we'll see that as we go through it. But importantly, today, we're going to talk about basically what happens if my data isn't linear, right? So what happens if I try to predict my line, or I try to predict, my data here using a line, but now remember, we're no longer using R as an indicator here of how good this fit is. But if I see a pattern, oh, that didn't work. If I see a pattern in my residual plot, right? So if I see a pattern, right, that's my giveaway here that I have a problem and it's not what I want and I want to use another model, right? So the first thing that we think about here, we have 4 different options, believe it or not. And depending on what your data looks like, will determine which one you use here. Right, so our first option, right, so our option number 1 is to look at x versus, instead of y, the square root of y. Right, so I'm going to take the square root of all the y values. And obviously here, right, this would be, if I have a quadratic, this might work out, right? This might transform it to make my data linear. Now, again, another important thing here to reiterate, you notice that we only use linear regression. Right? I'm not going to jump to a quadratic regression. So instead of changing our regression equation, we try to change the data to make it linear, right? So this is the first option, right? This is the first thing I'm going to try, mostly because compared to the other ones, this is just the easiest one to work with. Now, an important thing to keep in mind here, if this is the transformation that you make, is that what you're predicting now with your model is no longer the y value. It's the square root of the y value. So if you're trying to work backwards to what the actual prediction would be, we're going to end up having to square something at the end, right? So a very important thing to keep in mind here is that my equation now is that the square root of y equals mx plus b. So this is what I was talking about. So if you're actually trying to make a prediction back to the original question, we need to remember at the end to square our result, right? So if my model predicts 4, well, really it's predicting 16. Next, right, my second step here, I'm going to look at the reciprocal, right? I'm going to look at 1 over y and see if that helps, right? So first thing I'm going to try is this number 1. I'm going to take the square root of all the y values. If that doesn't work, meaning I still have a pattern in my residual plot, then I'm going to move down the ladder here and try this model. Now, again, important thing to remember, when making a prediction, what you are predicting is not the y value, but the reciprocal of the y value. So if your model is predicting 1/5, well, it's actually predicting 5, right? Take the reciprocal of that, flip it over. Right, I will say the biggest mistake people make here is on these steps. They forget that their model is predicting something other than just the actual y value, so they forget to take that extra step to undo what their model has done. Right, and so let's say, right, 1 failed, 2 failed. Well, the next thing I'm going to do is try and take the natural log of the y values. Now, it doesn't have to be natural log. It could be any logarithm. So you could use log base 10, and that's fine as well. I picked natural log for a couple of reasons. One is it's short, and 2, you never have to remember what base, because it's always base e. Right, so this is most likely if we have an exponential model, right? If your data originally could be modeled by an exponential, this will help to undo that. And again, very important here, what you're predicting is the natural log of y. You're not predicting y. So again, at the very end, we need to make sure that we take that and we undo it, right, by raising my prediction, right, to the power, or e to the power of my prediction. And then my very last resort is to take the natural log of x versus the natural log of y, right? And so this would be some power, in this particular case, other than 2, right? So a cubic, a quartic, a quintic, so forth, so on. We have some data set that is some other polynomial power, right? And again, very importantly here, this is going to be the natural log of y equals m times the natural log of x plus b. I apologize if you can hear the motorcycle going by my house right now. So again, in making our prediction, we need to make sure we raise that final prediction, right, as an exponent on e. So these are my 4 options as far as predictions, or transforming things to make predictions. So again, though, remember, right, I go here if there's a pattern, right? If there's still a pattern, I go here. And then if there's still a pattern again, I go here. And if there's a pattern in all 4 of these, well then maybe there is no best model, right? Maybe my correlation is never going to get better, and this situation can't really be modeled by anything that we know about. Right? Now, for the context of the AP exam, that's not going to happen, right? They'll give you something where creating a transformation is going to create the residual plot that you're looking for. They're not going to give you a question and say, transform the data appropriately, and then you cannot do it, right? So it's also a matter of making a judgment call, too, about which residual plot is the quote-unquote best in the given scenario. So just to take a look at what this looks like, right? And we'll do some more practice with this in class next week as well, just so we get a little bit more comfortable with it. I have this Desmos model here, right? And you can see pretty clearly, if it wasn't blatantly obvious, that this data is probably not going to be best modeled by a line, right? I actually modeled this table off of x squared minus 3. So obviously playing around with the numbers a little bit so it wasn't perfect. But overall, if I try and create my regression here, you'll see very quickly that it's not the best, right? So there's my line. And if I plot these residuals and I take off the line for a second, yeah, right? That's a pretty clear pattern in my residual plot. So what I'm going to do, first thing I'm going to do here is I'm going to get rid of this, right? And I'm going to set up my iPad here so I can type a little bit, right? And so now what I'm going to do, right, again, first resort here is instead of y1, I'm going to take the square root of it. So now I'm going to take here instead square root of 4. Oh boy. Square root of 4. And then I'm going to do this for each one of these, right? Square root of 7 here, right? Square root of 10, square root of 18, square root of 28, so forth, so on down the list here. And what I'm looking for is, at the end here, is my residual plot better? Now, obviously, I got to zoom in here. Now, to me, that definitely looks better. If you actually look at how our r and r squared changed, well, they got closer to 1. Now, granted, they weren't very far from 1 to begin with. But now if I, right, look at this equation, I look at this residual plot, turn these off for a moment and zoom in, so it looks better. Now for me, and it's kind of difficult, with only 9 data points, it's going to be hard, like everything potentially may look like a pattern just because you don't have enough for it to potentially look totally random. But for right now, this definitely made my prediction better. 100% this residual plot has less of a pattern than the other one, right? I have some positives, some negatives, and there's not like a clear division. So square root made it better. I'm not totally confident in that, so I'm still going to try the other ones. But so far, that's definitely better than nothing. All right, so now my next thing, if you remember, it was x versus the natural log of y. So natural log of 4, natural log of 7, natural log of 10, natural log of, oh boy, what was this? Was it 12? Nope, 18. This was 12. Natural log of 18, natural log of 28, natural log of 40, not 49, so forth, so on. So again, right, I'm going to do the same thing here. And I'm going to see, all right, well, there's my regression. Does this residual plot look better? Definitely not. Right? I mean, I can just tell right now, but zooming in on that residual plot, there's no way that looks better than the first one. That actually looks worse than the first one. Right? So this has a very clear pattern to it, and that makes sense, right? This data wasn't exponential. I said earlier, right, I modeled it off of a quadratic, so it's really not surprising to me that the square root residual plot was the best one. Now, you might be asking yourself, also, we'll talk about this in a moment, what happens if I have some negative y's and I have this logarithmic pattern? So we'll talk about that. Now, I'm not going to take the natural log of x here compared to the natural log of y because, again, it's not exponential. It's not going to work. But the last one, right, 1/4, 1/7, and we're going to watch this residual plot change as we go here. And again, very clearly here, this residual plot looks not great either, right? So it's not surprising to me, in this case, if I'm trying to make a best judgment, that the square root one was the best judgment. I'm not surprised in the least here. I've been actually lied before. I modeled this off of not x squared minus 3, but x squared plus 3. So, not surprising. Now, there is one case we do have to take care of, and that's if I'm using a logarithm, what happens if there's some negatives, right? If I have negative x values or negative y values. Now, if that's the case, an exponential model may not be the case, right? Typically exponentials, granted, if your a is positive, if you don't have a vertical shift, all of these things. But importantly here, let me make this in pink so it can be seen, right? If we have a y less than 0, we set it equal to half the smallest positive. Now, you might be asking yourself, why do we do that? And that's a great question. I don't know the answer to that. I've looked into it a few times. But the biggest thing here is we're trying to do anything we can to try and transform this so we can at least use a line. And I don't want to just ignore the data that's negative if I'm using a logarithmic transformation. So what this does at least is it keeps the data in the same place, right? Those negative values tend to be smaller as it is. And so by setting them equal to half the smallest positive one, they at least still remain the smallest data point. So I'm going to leave you guys just a short worksheet with a few examples to work on this transformation piece. Please turn it in just so I can give you some feedback and some credit for it. And I hope you guys have a wonderful weekend. I'll see you next week. Bye, guys.